Hello, I'm just waiting to make sure it's working. I know you're on a delay, so. Oops. Okay, I think it's working. Okay. You guys had a lot of questions on here. I was a little surprised, but we'll go for it. I tried to organize them in a way that I could kind of talk about similar things together. That way it makes things hopefully a little bit easier. So I think it's working. Oh. My iPad here is thinking really hard, so I just want to make sure it's working. Okay. All right. My question's up. All right, looks like we're going to start with ionic compounds and lattice energy. So let me see if I can screen share here. Okay, I believe you are seeing my screen now. So lattice energy is where I'm going to start with, and that has to do with ionic compounds. I didn't look up all the textbook questions yet, but I will. So which has the strongest lattice energy? Let me start with what the heck lattice energy is. Lattice energy is basically intermolecular forces. Lattice energy is the energy that holds these ionic compounds together. And you think about what holds ionic compounds together are ionic bonds, the intermolecular attractions of ionic bonds, or you can even think the ionic bonds themselves. Yeah, okay. So we'll start with the first one. Which has the strongest lattice energy, Na2S or MgS? So the sulfur is the same, so that's something to look at. Na and Mg are both right by each other on the periodic table. Na is number 11 and Mg is number 12 on atomic number. So that really says they're about the same size, which is what this person talked about. It's up my time here, 19-ish. So the only difference between there is their charges. Na has a +1 charge, and Mg has a +2 charge. So since they have different charges, that's kind of like different magnets. And Na+1 has really like a +1 magnet. It's kind of a small magnet. But Mg2+ is like twice as good of a magnet. So Mg2+ being a better magnet, a stronger charge, it can hold onto the other ions around it. An ionic compound, the Mg and S, let me draw a picture here. So Na2S, this is a +1 charge. Mgs is a 2+ and a 2-. This is a 2-. The sulfur is really the same, so it's just our Mg and our Na that matters, and the size is the same. So Na being a +1 is like a smaller magnet than Mg being a 2+. And in a lattice energy, or a lattice kind of compound, you've got all of the, we'll call them balls, or really ions that are around each other, Mg2+, right next to the sulfur 2-. Maybe I could get some better ratios here. And so this 2 + 2- has a really strong attraction to each other, no matter which way I start to attract them, no matter which way the Mg goes. With an Na2S, you've got NAs next to an S. We need 2 NAs for every 1 S. Put another Na down here. And so the lattice energy is this energy between any Na and S, whichever way you want to go. And the lattice energy isn't going to be as strong because the Na has a smaller charge. Smaller charge means it's got, just in this case, it lost fewer electrons, and that makes it weaker. Not as strong of attraction, weaker lattice energy. Okay, there's that one. All right, So let's go to question 3 on page 236. I want to read the question fully before I answer it. Question 3. Okay. So we'll talk about this one. So for those of you who don't have your textbook with you, I'll kind of show you what it's talking about. The choices are BaCl2, LiF, NaBr, and Ki. And it says, which one require the most energy to break the ionic bonds? Which one require the most energy to break the ionic bonds? Which is basically asking is which one has the strongest lattice energy. Well, between all these choices, the first thing I'm going to do is look at charges. Ba is a 2 plus, Cl is a 1 minus. Li is a 1 plus, F is a 1 minus. N is a 1 plus, Br is 1 minus, K is a 1 plus, I is a 1 minus. So if you look at all of the choices, they're all 1 plus and 1 minus, except for this top one is a 2 plus and a 1 minus. So that should scream that this is going to be an ion kind of situation where the charge is different. If I had to pick one way or the other, I would say a charge is more important than the size. Because when we talk about size, we're looking on like the really, really teeny tiny level. So an atom, you know, is this size or just a little bit bigger. I mean, the size doesn't make that big of a difference. When you look at it, not as big of a difference as a 2 plus and a 1 minus sort of thing. Now, is that true always, always, always? No, but that's what I would go for. So the first thing I would do when I answer one of these questions is to look at charges, because that's the easiest way to go. And since the atomic size really changes, but not as drastically differently, it's going from a 1 plus to a 2 plus. So in this case, BaCl2 is a stronger lattice energy. And it's an easy one to pick because it's the only one that's different. Okay, 2 is the next one. Why is it that atomic radius increases, the melting point decreases? Let's do this one a little later. Right down here, kind of. Okay. In the textbook homework, why would MgCl2 be the right answer on page 234? Boop, 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 boop. So I think they copied it. I'm going to read the question just in case. Yeah. This one's another case where you're looking at ion charges. So if you do the ion charges for all these, Na is a 1 plus, oops, and Cl is a common factor here, so that doesn't matter. K is a 1 plus, Mg is a 2 plus, and so because of that, you can see the ion charges are much different. So yes, it would have a stronger lattice energy, just like what I talked about for number 2 above. 2 plus is a much bigger magnet than a 1 plus. How can you explain lattice energy and relate this to physical properties of ionic compounds? Okay, if I remember right, this is one of the objectives. This I can hit a little bit better when we talk about properties right down here, because lattice energy really is like the intermolecular forces that hold an ionic compound together. So anytime we talk about intermolecular forces, we're talking about lattice energy. And anytime we talk about intermolecular forces, we're talking about physical properties. Physical properties are things like melting point, solubility, things you can do to the compound that doesn't change what the compound is. It's not a reaction. It just changes how the compound looks. So I'm going to continue this question. With the properties topic that I'm going to talk about below, because this properties topic have to do with intermolecular forces, which is really a lattice energy. So I'm going to go down there. And I think I'm going to bring this one down there too, because it has to do with melting point. Okay. So let's start with properties then. Okay, how does surface tension evaporation relate to a compound structure? Is it how strong their bonds are? We have to be really careful about this word bonds, You can't say the word bonds because that implies it's an intramolecular force that you're implying. And when we're dealing with surface tension and evaporation, we're only breaking intermolecular attractions. So let's take a look at surface tension and evaporation and talk about their structure. I'm going to draw a picture with that. Okay. So let's say you have a high surface tension. That means you can put a lot of drops on the penny versus a low surface tension. If we take a look at surface tension itself, like water, surface tension is strong when each of these water molecules are attracted to its other water molecule friends. We know that water has hydrogen bonds, and hydrogen bonds are a really strong intermolecular attraction. So if they're a strong intermolecular attraction, they're going to be attracted, the waters, to each other, and that creates a high surface tension. Now, hydrogen bonds aren't the strongest kind of surface tension. The strongest kind of intermolecular force, really, I should say, are the ionic. The intermolecular attraction of ionic, which would be really the same thing as lattice energy. The stronger the lattice energy, the stronger the ionic intermolecular attractions, therefore a high surface tension. So to that person question that I just kind of skipped over briefly, here's lattice energy coming back. And anytime I say the word ionic, it really is going to be the same thing as lattice energy. So keep that in mind. We also know that if we have hydrogen bonds, the thing that's weaker than hydrogen bonds in intermolecular forces are dipoles. So if you have something like HCl, which is a molecule that has, it's a polar molecule. So these two would be attracted to each other. Maybe a little better if I didn't draw the two negative signs lined up, but here, there's some attraction. These two are attracted to each other right between there. One side's positive, one side's negative. That's our dipole attraction. So they're going to have a pretty good surface tension, but not as strong as a hydrogen bonds or an ionic one. And then, of course, the lowest is going to be our dispersion forces. Now, if we go into evaporation, and we take these same intermolecular forces, like hydrogen bonds and dipole and dispersion and ionic, if we look at those same intermolecular forces, we can relate evaporation in the same way. Let me do some erasing here. So evaporation is the idea of going from a liquid to a gas. And in order to go from a liquid to a gas, you have to break intermolecular attractions. We know liquids are attracted to their friends. We're right next to each other. But as a gas, there are no attractions. They're really spread out from each other. So the more you love your friends, like we'll take hydrogen bonds again. If we look at hydrogen bonds, the more you really love your friends, like something waters, next to waters, they very much love their friends because they have a strong hydrogen bonds. It's going to be really hard for them to evaporate because they love their friends so much. So if we're looking at the rate of evaporation, the speed at which they evaporate, something with hydrogen bonds isn't going to evaporate very fast. So the rate of evaporation for something with hydrogen bonds is really slow. It's going to be hard for them to evaporate. And if you think about ionic compounds, I don't know about you, but table salt and how fast it goes to a liquid and then evaporates is extremely slow. Its rate of evaporation is extremely slow because it loves all of its friends. Which means down here, anything that has dispersion forces, they don't love their friends very much. Therefore, their intermolecular forces are really low, and they can quickly evaporate and become a gas and leave their friends. Okay, so I think that covers that one. Okay. Okay, we'll look at what's the next one? 832. Ionic compounds can only conduct electricity when they're liquefied or dissolved in water. Yes. Metals can conduct in any form. Yes. Molecular compounds only conduct when they're dissolved in water. No. So in order to conduct electricity, you need two things. One, you need charged particles. And two, they need to be free to move. If you look at ionic compounds, they always have charged particles every single time, but they are only free to move when they're liquefied or dissolved in water. Metals have charged particles, those electrons that kind of fly around, and they can conduct at any time. Speaking of which, let's do this one. We'll put it up here with it. We're going to talk both of these at the same time. Okay, I'll draw you a picture. So, in order to conduct electricity, you need charged particles, and they need to be free to move. Those are the two requirements in order to conduct electricity. And you can reread that in the article that I have posted on my website. So if you look at ionic compounds, the second question below is how do you draw an ionic bond? You can draw it many different ways, however it works for you. I like to think of it as a cation. That's a positive ion. That says cation. Next to an anion, which is bigger, is the negative ion. The ionic bond is the attraction that is felt between this cation and this anion, the plus and minus attraction. Just like all intermolecular attractions are the idea between the plus and the minus. In this case, I have a permanent plus, the cation, and a permanent minus, the anion. Well, if I look at a metallic bond, yellow's kind of a weird color. In metallic bonds, I've got these cations, and now they're not really cations because cations are permanently charged particles. This is just kind of like, they call them cations in quotes because they're just the nucleus of the metal. So if you take the innermost electrons and the innermost nucleus, that's what these little plus parts are. Not the outer energy level, it's the inner energy levels. The outer energy level has electrons in it, and those outer energy level electrons are these guys. They get to fly wherever they want. So let's say technically this electron belongs to this atom. Well, he can kind of fly wherever he wants. Now that electron is over here. So that's the beauty of a metallic bond. They kind of share their electrons everywhere. And a metallic bond is this whole picture that I drew. So if we look at how do things conduct electricity, ionic compounds conduct electricity when they're liquefied or they're aqueous. And I know that because ionic compounds are charged, but they're only free to move as a liquid or aqueous. So that's why ionic compounds have to be in that state of matter. When we look at metals, they can be in any state of matter because, that's a Y, any state of matter, because they have these free moving electrons, no matter if they're a solid, a liquid, or a gas. If you look at molecular compounds do not have any charges. Yeah, they have partial negative and partial positive, but that's not enough to actually conduct electricity. In order to conduct electricity, you must have a charge. And molecular compounds have no charge. If they have no charge, they can't possibly conduct electricity. You don't have to worry about free moving. They don't have a charge. They cannot conduct. Okay, choose the next one. Melting point. How does the state of matter relate to the compound structure? That has to do with melting point. Okay. All right, here we go. Let's talk about melting point. Okay. All right, thinking about when something melts. When something melts, it goes from a solid to a liquid. So if you think about things as a solid has to be really stacked up on top of each other. They're just put together. You can think of an ionic compound, molecular, any one you want. As a liquid, they're no longer strictly in one set path. We know liquids take the shape of their containers, so they're kind of like flying by each other. They're still all touching each other, but they're moving a little bit faster and they're moving away from each other. So in this way, if you think about the intermolecular attractions, as a solid, you have a really strong intermolecular attraction. I'm going to represent the intermolecular attractions with a heart, because that's really what it is. The plus and minus parts, however big the plus and minus parts, are attracted to each other. That's an intermolecular attraction. Here, this one and this one in the liquid, they're still attracted to each other, but they're moving so fast that it's a small amount of time in which they are attracted to each other. So in a way, what you've done is you've kind of broken down or torn apart the intermolecular attraction, the love, if you have it, between the compounds. So in order to melt, you have to sort of break the love or the intermolecular attractions. Now you're not fully breaking them because they're still attracted to each other, but you are breaking it down. You're having the attractions be less time. So that means if you love your friends more, if this intermolecular attraction is a lot more love, you're going to have to be going pretty fast in order to break that amount of love. Because they're still loving each other over here, but it's just not as much time. So in other words, the higher the melting point means the more you love your compound friends. Okay, so I need a new screen here. So looking at melting point, if you have a high melting point, that means it's really hard for you to leave your friends. That means you have to be going really fast to break all of that love that you have. Something that really loves each other would be an ionic compound. Ionic compounds are plus and minus things. They really love each other. They have a strong intermolecular attraction. Something with a really low melting point would be something like dispersion forces. They don't really love each other. I mean, they kind of have a positive and kind of have a negative, but kind of not. So really, they don't love their other dispersion force friends. So they will have a low melting point. It won't take them to go very fast in order to leave their friends and no longer be melted, no longer be a solid. I don't remember what all my questions were going to be now that I think of it. Oh, where did my screen go? Oh, I guess I gotta get back again. Here we go. Okay, so how does sigma relate to a structure? I think I covered that. A higher melting point and no associated charges. Okay, I think I covered that. How does aluminum have a medium? Okay, I'll talk about that one. And then I'll talk about this one too. Okay. So, like metallic ones, what does that all fit in? Well, ionic is a plus and minus for sure. The next one would be hydrogen bonds, perhaps. And a hydrogen bonds have an intermolecular attraction that's pretty strong because they are a pretty set plus and minus. They're a super dipole. Dipoles are in here. So I would have to say that I would call these medium in a way, and this one really high, and then this one really low. But we do have to consider metallic bonds, and I would say metallic bonds also come in here. And I would put metallic right in here. I would call them medium, I guess, in some way. So all the middle ones are kind of medium, but metallic is right in between your hydrogen bonds and your ionic bonds. And the reason for that, I know metallic bonds are kind of funny to think about. If you think about a metal, one, it's always a solid at room temperature, which means its melting point must be pretty high. If you think of something with hydrogen bonds like water, it's a liquid at room temperature, which means its melting point had to be a little lower than that. So metallic bonds, since metals are always a solid at room temperature, except for mercury, that must mean that they're going to have a pretty high melting point. They must have a pretty strong attraction to each other. When you think about a metallic bond, it's all these plus things, and they are permanently pluses, kind of attracted to all these minus things, and they are permanent minuses. Hydrogen bond is still a sharing of electrons. It's still a probable positive and negative side. It's still a partial positive and partial negative, but it's not a set positive and negative, like a metallic bond is. That's why I would stick metallic bonds up in this point, in the melting point of just below the ionic compounds. They have a pretty high melting point. Okay, and the last one here. Why is it that atomic radius increases, the melting point decreases? Okay, so melting point, once again, is talking about these attractions that you have to each other. So when we're looking at the size of the atom, that's what I'm assuming that they're looking at. When you look at atomic radius suggests we're looking at one atom, and if we're looking at one atom, that makes me think that we're looking at ionic compounds. So I'm kind of interpreting this question. So we're strictly looking at ionic compounds now, and we're looking at its melting point. So once again, we've got to think about how much they love their other compound friends. So if you have, oh, that's a really big plus guy, that's okay. A cation attracted to an anion, and these are its charges. And then I have a cation trying to make it the same size as the one above there, but I kind of failed at it. Attracted to an anion. Okay. We're going to look at this attraction right here, which is technically the intramolecular force, but in an ionic compound that you can't tell the intras from the inters. So really every intramolecular force is between a cation and anion, and every intermolecular force is between the same cation and the same anion. So we're really looking at how much love these two feel versus how much love these two feel. You can see the only difference I have here is the size of my anion. Now the cation's power, since it's positive, comes from the nucleus, so it's centered in here. Oh, this should say cation, what the heck? There we go. This cation's power is centered in the nucleus also because he's positive, and positive things happen to live in the nucleus. Now if we look at the negative ion, the negative power comes from all the electrons that live around here. So if we look at this anion and where it's all centralized, all the electrons are kind of spread out fairly widely, and so the force of attraction that it has isn't as compact. If you remember looking at the size of the atom and thinking about like the Power Rangers idea, that they're stronger together than they are alone, you can see these electrons aren't very together, so they're weaker. So this love or this attraction that it feels is from the nucleus to the outer ring part, but it's weaker than this bottom one here, where you have these electrons. And they're all centralized in there, so the power comes from that proton's part to the outside, and that's going to be a stronger attraction because there are more negative parts in a smaller region. They can hold on to each other better. They're stronger together than they are alone. They're more compact. It's easier to think of it on the cation side. If the cation is this big, or the cation is this big, and then we think about how much attraction it feels to its negative anion, which I'm trying to make the same size, you can see the power that this one has to send all the way out to the negative part. That's a long distance. That's not very much love. While this one has to send out its power only this far. That's a lot more attraction. One magnet that's really far away from its other magnet isn't feeling very much magnetic power. But one magnet really close to the other magnet is feeling a lot of power. Hopefully one of those pictures helped you. So in other words, back to melting point, before I go too far here, the more attraction you have, so these bigger heart parts, the more attraction you have, the higher intermolecular attraction you have, the higher the melting point. Because melting is when you have to slightly break down, quote unquote, break down intermolecular attractions to become a liquid which is less intermolecular attracted to each other. Okay. How does boiling point relate to the physical properties of the compound to their structure? Boiling is the idea that you have to go from a liquid to a gas. And if you have to go from a liquid to a gas, you're going from an intermolecular attraction as a liquid to a gas where you're not attracted to each other at all. So you have to completely break any attraction that you have. If you're really attracted to your friend, it's going to be pretty hard to boil, and you've got to have a high boiling point. They have to be going really, really fast to even have a chance to leave their friends. So boiling point is really the same as melting point. It's just going from a different state of matter. All right. Intermolecular attractions here. I'm going to put this here. Oh, in here. Okay, so most of these questions go back to the previous, well, I mean this chapter, but they relate all to the previous test that we took. Numbers all jumbled up. Okay. Looking at this one, 8. In hydrogen bonds, do both H's need to be attached to an F or an N? Or does only one? Yes, both. Otherwise, it's not a hydrogen bond. Otherwise, it's a hydrogen bond / dipole-dipole attraction, which isn't as strong as a hydrogen bond. Next one, 849. How do you know if a compound has dispersion forces? What do we look for in a structure? So dispersion forces only happen when it's a temporary dipole that's created by the electron cloud being temporarily distorted. And the only way that an electron cloud can be temporarily distorted is if it's being sharing its electrons. So the first thing you need is you cannot have an ionic compound. Ionic compound isn't temporary. It is plus and it is minus. Dispersion forces are temporary plus and minus sides. So how do you know if a compound has dispersion forces? Well, any molecular compound will have dispersion forces. So you find a molecular compound, it will have dispersion forces. 849. How do you know if an element is a dipole-dipole? The first thing on that part, it's not an element, it has to be a molecule. So I'm going to add that to it. An element can't have dipole-dipole because in order to have dipole-dipole, you have to have a polar bond, and only molecules have bonds, not elements, so therefore it has to have, so it has to be a molecule. I know that's nitpicky, but I thought I'd do it anyway. I know that you can find it by being polar, but how do you find that? Okay, so this is going to be a really brief on how to determine if something's polar or non-polar, but I do have a video on my website. So to anybody who needs more on this question, I would definitely look at my website videos on that. I think I have one on polarity. If not, I'll look for it after this video just to make sure. Okay. You have to decide if a molecule is polar. So the first thing you need to do is you need to draw the the Lewis dot structure. So I'll do the Lewis dot structure of CH3I. I know you guys know how to do Lewis dot structure, so I'm not going to talk too much about that. Boop. Okay. The second thing you have to do is consider the Vesper structure. So in this case, I've got a tetrahedral. And with a tetrahedral shape, yes, you will get the Vesper chart on the test. With the tetrahedral shape, this isn't the best 3D drawing, but it's not terrible. They kind of do a little zigzag. So if I draw it here, all of the atoms are 109.5 degrees away from each other. Yes, I think that's right. And so it makes it close, but not exactly what the structure is. So you would want to draw it in 3D if you can't think it in 3D. If you can think in 3D, you're okay. Step 3 is to use electronegativity and find the polar bonds. So polar bonds are things that happen with the electronegativity difference of 0.4 to just below 1.7. So less than 1.7 and greater than 0.4 in difference in electronegativity. I don't know iodine off the top of my head. Can I make it up? No, I got my textbook here. I'll do it. I'll do it. .66.
Carbon is 2.55 and hydrogen is 2.2. Okay, so I asked myself, do I have any polar bonds? That means look at each part. This I to a C is only a difference of about 0.1, so no, that's not a polar bond. The C to an H is a difference of only like 0.3-ish, so no, that's not a polar bond either. So I don't have any polar bonds here. And the fourth step is to decide, do you have partially positive and partially negative sides? And how I kind of taught you that is, does the molecule move? Which doesn't work 100% of the time, but most of the time it does. In other words, if I had any polar bonds here, I would look at a tug of war. Now, I don't have any polar bonds, so in that case, I can't consider does it move or does it not move. And then I'd also want to look for regions where it's a kind of positive, kind of negative. Well, all of these are sharing electrons equally, so I don't have a kind of positive, kind of negative. The electrons are shared equally everywhere. So if I draw a circle around this molecule, there's no part of the circle what I would do negative and no part of the circle that I would do positive, because they're sharing electrons equally. This is a nonpolar compound. It has nonpolar bonds, and it is a nonpolar compound, which means there are not two ends. All electrons around the molecule are shared equally. If I wanted to do a different drawing, one thing I could do is just stick a BR, I think. Yeah, I'll stick a BR up here. A BR is 2.96. That makes this bond difference, 2.55 to 2.96, is greater than 0.4. So I would have a polar bond. And that would be one tug of war moving upward, which would mean that this molecule is suddenly polar. What that really means is that this top side of the molecule is kind of negative. The bottom side of the molecule is therefore kind of positive. And I know that based on this polarity arrow. So that means that there is one polar bond, which means they share electrons unequally. And altogether it is a polar molecule. And I know this because the electrons tend to live around the bromine more often. All the electrons are kind of shoved up that way. And in that sense, since they all live on the top there, this side of the molecule is kind of negative with a high concentration of electrons. The bottom side of the molecule is kind of positive because it's kind of electron deficient. It doesn't have as many there. So therefore I created two poles, two ends, a plus end and a minus end, which is what polar means. So those are your quick 4 steps on how to decide if something is polar. And if something is polar, then you have dipole-dipole attractions. That's all you have to look for when something is polar. And if it has dipole. Okay. How do you know when the number of dispersion forces adds up to more powerful than a dipole-dipole or hydrogen bond? By looking at data. That's how you would know. When you look at it and be like, wait a minute, but this, like in our Motorola one, you looked at it and you're like, but that doesn't make any sense because that one just has dispersion forces and that one has dipole-dipole. Dipole-dipole is more attractive than dispersion, so it shouldn't work that way. Well, if the data seems a little funky-dunky, then that's a case where dispersion forces really do matter. They make a huge difference. So that's how you can tell. Otherwise, you really can't. You can kind of infer, you can kind of guess and kind of predict, but you can't know for sure unless you look at data. Whew, 856. How do you know if water will be attracted to a compound? Any attractions that happen is because of plus or minus things. So when I'm looking at intermolecular attractions and I want to know if something is attracted to something, I'm going to look for plus and minus parts. Water has extreme plus and minus parts. It has hydrogen bonds. So what will water be attracted to? He's going to be attracted to something else with plus and minus parts. Ionic compounds have plus and minus parts. He'll be attracted to that. Dipole-dipole has plus and minus parts. So he'll be attracted to that. Hydrogen bonds has plus and minus parts. They'll be attracted to that. Dispersion forces has plus or minus parts. So it'll be kind of attracted to it, but really not that much. So it kind of looks to its water friends and is like, meh, I'd rather be with water than with you, Mr. Dispersion Force 1. So he's attracted, but really not enough to do anything. And that's why we don't have, that's why with something with just dispersion forces can't dissolve in water. Because water is like, you know, you're attractive, but not as much as my other water friends here. So I'm not going to surround you. I'm not going to be attracted to you enough to surround you and actually dissolve you. Tomorrow on quiz, if you had to talk about this attraction thing, I kind of like briefly summarize it by talking about like these plus and minus parts. You can't just say on the test like, well, if water has plus and minus parts, then it'll be attracted to plus and minus parts. You have to explain what those plus and minus parts kind of mean
talking about how water has oxygen and hydrogen. This is a polar bond. These polar bonds create a polar molecule, which means that the electrons are shared unequally amongst the water molecule, and therefore electrons live around the oxygen more often, which creates a partially negative side of the oxygen, and the hydrogen is electron deficient. The electrons don't live there as much, which means that the hydrogen side is partially positive. This creates a partial negative, partial positive of water, and those partial positive and negative sides can be attracted like magnets to other compounds. That'd be a better way to say it. Okay, well, 8:58. I made it for my 9 o'clock goal. There we go. I'm going to try to pretty up this document for you. Hello, you can watch me. I'm going to see if anyone types to me in the next 2 minutes here. And then, yeah. I know you're on delay, so I'll wait more than 2 minutes. I'm putting all my stuff in red. Somebody's typing this. Yes, water can be attracted to something other than hydrogen bonds, anything that has plus or minus. That's why ionic compounds dissolve in water, because water is attracted to the cation and surrounds it with its oxygens, or it's attracted to the anion and surrounds it with its hydrogens. And that's how ionic compounds can dissolve. So yes, water can be attracted to something other than just hydrogen bonds. It's attracted to those partial negative, partial positives, or the set plus and minus that ionic compounds have. Another question for you. You watch me open my nail. All right, well, I think I might be signing off here. As I can see, I just filed my stuff. That was a really exciting part of the video. Awesome. Okay. Good night, all. I'll see you tomorrow. Get some sleep.